Hi, my name is Sarah VestalS, and the focus of my research this summer was an analysis of upper extremity joint kinematics and surface electromyography. My work is contributing to an ongoing study between Bucknell and Geisinger to identify individual kinematic synergies that are linked to individual electromyography synergies in healthy adults, with the end goal of improving stroke rehab. Strokes are the leading cause of disability in the U.S., with about 80% of stroke survivors experiencing movement difficulties. Rather than controlling muscles individually, the human central nervous system adopts a modular control strategy, thus making control of the whole musculoskeletal system more efficient. These groups of muscles are referred to as muscle synergies. Muscle synergy-based rehab has had success in restoring impaired motor modules, but is costly and unavailable, so identifying kinematic motions linked to EMG synergies would eliminate the need for expensive equipment. The majority of my research is centered around data collection, processing raw EMG data, and developing an approach to performing inverse kinematics using an upper extremity model. When subjects come in, they're outfitted in 19 EMG sensors and 25 reflective markers, then told to perform a series of upper extremity movements to mimic daily activities. We then take the marker trajectories and import them into OpenSim model to perform inverse kinematics, which is the process of calculating joint angles and positions in a model corresponding to the experimental motion data. In figure 2a, you can see two different models that were being considered for this experiment. The model on the left is what we started with, but it only has 3 degrees of freedom in the shoulder, so we are now working with the model on the right, which is more anatomically correct as it accounts for both the 3 rotational degrees of freedom in the shoulder as well as translations in the joint center. In 2b, you can see large differences in the axial rotation of the shoulder and movement as simple as zipping up a jacket, so we are confident that this new model will provide more accurate results. The next step is to process the raw EMG data. As seen in figure 3a, the raw signals are very noisy and it isn't clear what's going on, so we must filter, rectify, get the root mean square value of the data, then normalize it to create a relative scale for comparing signals. Figure 3b shows what the same data looks like after processing, and as you can see, sensor 9 in black is being activated, while sensors 1 and 2 were not. Our next steps moving forward are to complete data collection from 20 healthy adults and extract EMG synergies from that data. Figure 4 shows a simplified version of how muscle contractions are used to extract these synergies. Subjects will later be asked to generate an upper extremity movement that produces the same surface EMG profile as the EMG synergies using visual feedback. Then these distinct arm kinematics derived from the EMG synergy will be labeled as a kinematic synergy. Thank you for listening.